As you've been reviewing, we see that the Q for reaction is negative Q for the solution. In other words, the water absorbs heat as the equation releases heat. We understand that Q is heat energy, mc delta T, where a solution is a water-based aqueous solution, so we tend to use 4.18 joules per gram Celsius. The heat of the reaction is Q of the reaction. We're measuring it with a coffee cup calorimeter. So to get delta H for the reaction per mole, we've got to divide by the number of moles of our reactant. And let's just take a modeled example. We're on slide 29. That reads, what is the delta H of a reaction in moles of magnesium if magnesium solid is placed into aqueous hydrochloric acid, producing magnesium chloride aqueous and hydrogen gas? Our given is 0.158 grams of magnesium. We place that into 100 milliliters of solution, and the temperature changes from 25.6 to 32.8. Let's first solve for the heat being absorbed by the water, the solution chemistry. So Q is mc delta T, solving for the water first. The water is absorbing the heat energy as this reaction proceeds. So the mass of the water given to us is 100 milliliters, but keep in mind the density of water is 1, so instead of 100 mils, we'll simply convert that to a gram unit. The density of water is 1 gram per mil, so those are indeed allowed to be changed. That's not true for any substance, but it is for water. Specific heat constant for water we have memorized is 4.18 joules per gram degree Celsius. And the temperature difference, well, let's just hit that. We can see we would have 32.8 minus 25.6, so the temperature changed by 7.2 degrees. Solving for joules of energy that was absorbed by the water. 100 times 4.18 times 7.2. 3009.6 joules of energy absorbed for the water. Now think about what that represents. That's the heat change when 0.158 grams of magnesium reacted. We're being asked to report this value in moles of magnesium. So let's just do a little mole work. If 0.158 grams of magnesium reacted, let's simply convert that into the mole unit by using its molar mass. We know that 1 mole of magnesium, looking on our periodic table, we can find its atomic weight, and it's 24.3 grams. 1 mole of magnesium would weigh 24.3. So let's take our mass, 0.158. We'll divide that by 24.3, and that simply converts the gram unit into the mole unit, 0.0065 moles of magnesium. Now, friends, look what we have. We have joules of heat, and we have moles of magnesium. We're being asked to solve for the heat of the reaction, which is joules per mole. The delta H for the reaction per mole of magnesium is simply found by taking 3009.6 joules, dividing it by our mole number solved above, and just getting to the desired units of joules per mole. 3009.6 divided by that previous answer, the moles of magnesium, and we get a large number, 462,868, and I'll round 0.9 joules of energy. And that's reporting that in terms of per mole of magnesium. What might be a little easier for us to read instead of this large number is converting joules into kilojoules, which often delta H's are reported as. So 462, and I'll just round a little bit, kilojoules per mole would be a more common way to express that value. This number for joules was rather large. I slid the decimal 3 spots to the left to simply change the joule unit into the kilojoule. So when 0.158 grams of magnesium was placed into acid, it released heat. The heat that was released was absorbed by the water. Heat released by the reaction was absorbed by the water. The water absorbed, that's a positive sign. It absorbed 3009.6 joules. Therefore, the heat was being released by the reaction. I better show that I know that reaction to be exothermic and place a negative sign at the end. Heat absorbed by the water must have been released by the chemical change. Negative 462.9 kilojoules per mole. Let's try another. Perhaps you'd like to pause and try this one and then turn the video back on and follow. It reads, what will be the final temperature of a solution in a coffee cup calorimeter when 50 mils of a sample of hydrochloric acid is added to 50 mils of a sample of base? The initial temperature is 19.5 degrees Celsius, and the heat of reaction is 57.2 kilojoules per mole of sodium hydroxide. Let's just pause and see what they're really saying. The reactants, those things that are actually doing chemical change, the first reactant is hydrochloric acid, HCl. I'm placing that into a second reactant. It's sodium hydroxide, NaOH. When an acid and a base react, they neutralize. The pattern of change we called a double replacement. H goes to OH. We commonly write that as water, HOH. I'll write that as water. And sodium then hooks to chloride. We get NaCl. When an acid and a base neutralize, we come up with a salt and a water. A very strong pattern in chemistry, acid-base neutralization. It's telling us that 50 mils of the acid is being placed in with 50 mils of the base. They have equal volumes. Important to note here, the 0.25 molar solution of acid and the 0.25 molar solution of the base are extra numbers. They are not going to play a role in the chemistry. It's simply there to let you know they are exactly the same concentration, therefore no limiting or excess reagent. But this is an important number. When this reaction proceeds, it releases negative 57.2 kilojoules of energy for every 1 mole of sodium hydroxide. Well, the coefficient here in front of NaOH is indeed a 1. So negative 57.2 kilojoules shows the enthalpy change for this acid-base reaction. We'd like to know the final temperature of the solution. Well, here's what we know. We know the delta H for this reaction is 57.2 kilojoules. I need to write that in terms of joules of energy, so my MC